Hello everyone and welcome to the 2021 Astro Pi webinar. I'm Richard from the Astro Pi team here at the Raspberry Pi Foundation, and I'm here tonight with my wonderful friends and colleagues Olympia, George, and working away behind the scenes is Mr. C. So first of all, we just want to say congratulations to you all for having made it through to phase 2 of the competition. We had more entries than ever before this year, and they were all of a phenomenally high quality, which made the judging process really tricky. So to have made it this far through the competition is a real achievement. Well done to all of you. We've got quite a lot to cover tonight. So first of all, I'm going to hand over to Ollie, who's going to talk to you a bit about some of the logistics around your kits.
Hello. Before I start talking about the kits, I just want to give you all this email address. You can use it to contact us at any time, and throughout today's webinar, we're going to be asking for you to get in touch with us. And I know that there were quite a few teams that were asking if they can ask us technical questions as they're developing their projects, their programs. Use this email address, and the right people will be getting back to you. We'll repeat it at the end of the webinar as well, and this is being recorded so you can watch it as many times as you want. We've emailed you when we told you that you were successful in getting through to phase 2. We let you know that the kits, because of the volume of entries that we've had, that some of the kits are delayed in being sent out. We've asked you to give us an alternative delivery address if you're not able to receive deliveries after the 21st of December. If you could use that email address that I just provided with you to let us know which address, if you're going to be leaving, if the school closes, for example, before the 21st and won't be able to accept deliveries, you can send us an alternative address, but please do that by tomorrow, Friday, the 3rd of December. Someone asked if we know which transport companies. In the UK, we're going to be using DHL, and in the EU, we're going to be using UPS. You should be sent tracking links. Definitely all of the deliveries in the EU will be sent tracking links. And you can, again, email that email address that we've given you if you don't have, if you're worried about the delivery and want to get our tracking link. We can, if you just email us from the email address that you registered with and quote your team name, we can send that out to you. But the good news is that you don't need to wait until your kit arrives to begin coding. I'm going to tell you a little bit about how to do that now. So today, throughout the webinar session, we're going to talk a lot about the Missions Space Lab Phase 2 guide. There's a link at the bottom of this slide that will take you straight there. This document is the document that can be your Bible throughout the whole of Phase 2. It's got everything you need in order for your experiment to achieve flight status. In that Phase 2 guide, you can also get some recommendations about how you can begin your planning your program before your kit arrives. You can get your team together and start noting down all of the ideas of what your program will do. And then you can begin to order that plan and assign tasks across the team based on your strengths and experiences. There's also the Sense Hat and AstroPi emulator on Trinket to begin at trinket.io/sense-hat. Again, that link is in the Phase 2 guide. And you can research the libraries and data sources that you might use and map out a rough outline of how your team's program will work. We did have a question from one of the teams about how to push the buttons on the Trinket emulator. That's actually not functionality that's on there because your project can't rely on astronaut interaction, i.e. an astronaut pressing buttons during the running of your 3-hour window. We have disabled that functionality, so you won't actually be able to use buttons. If you want to adjust the temperature or the pressure, for example, to see how your program responds, then you can do that with the sliders up at the top. George later is going to talk about the checks that we make on your programs when we have received them, but there are also lots of checks that you can do before you submit them. The Phase 2 guide has a checklist for you to complete before submitting, and that can be found at this address. That takes you straight there, though it is in the Phase 2 guide and is at the end of that. So if you're working through your phase 2 guide, you will come across it. I'm going to hand over to Richard to talk about your hardware and kits.
Thanks, Ollie. So yeah, so the exciting thing this year, of course, is the new hardware. So this is an old Mark I flight unit there. You can see it's a bit different. It has 4 buttons at the top there. It doesn't have anything particularly interesting at the back, just this blue filter over the camera. Our new hardware, of course, is much grander. It's got this really big lens at the back that you can see that will enable us to take even better pictures of the Earth. And I'm going to talk a bit more about that later on. And also you'll see at the front, some of the buttons have gone away, and we've got at the top here, on the side, we've got the PIR sensor. So the PIR sensor is one of the new things we've added into the hardware. And also down here on this side, you've got behind this little window, just below the joystick, is where the color sensor lives. So that's a new sensor that's been added in to the SenseSat, a special version of the SenseSat that's being sent to the International Space Station. And when you receive your kits, you'll find that you've got one of those very unique custom SenseSats as part of your kit as well. In terms of the hardware, it's put together very much in the same way as the previous kit. You've got a Raspberry Pi inside, you've got a SenseSat, and you can see how it all fits together on this graphic on the screen at the moment inside that lovely case. We've had quite a few questions about cases, which I'm just going to try and deal with some of those now. First thing was about the motion sensor and how sensitive it is. That's quite a difficult question to answer, and it does depend on the environment that you're using the motion sensor in. It's worth remembering that the motion sensor, the PIR you get in your kit, is different from the one that's actually on the front of the flight unit at the top there. What I'm going to do is I'll put in the chat a link to the technical specification of that PIR, and you can have a look on there, and that will give you some actual figures around the sensitivity. But it is worth saying it really will depend on what's going on around you, how far away things are, and just the general busyness of the environment as to how sensitive the SenseSat is. We've also had quite a few questions about 3D printing a flight case. Now, in order to do Mission Space Lab, you absolutely don't need a 3D printed flight unit at all. Everything you get in your kit is enough to run your experiment, but I know that is really popular, and it's actually one of the things I've been working on recently. I've got a prototype 3D printed case here that you can see. It's not quite ready for release yet. There's still some things we need to work out to make sure it prints really well, because obviously the files, the CAD files this is based on, are the ones that are used to mill the flight units out of aluminium, not to 3D print them. So there's quite a bit of adjustment we need to do to make those really easy to print. So they are on the way. They should be available hopefully within the next couple of months. But just to emphasize, you don't need those files in order to take part in Mission Space Lab or to start the design and working of your experiment. Oh, I didn't want to do that. I want to do this. So the other thing that's new about our hardware this year is the Coral machine learning dongle, which comes with the flight units and is attached to it. And now George is going to tell you a bit more about that.
Yeah, hi everyone. So the Coral is one of the new pieces of hardware, and along with the camera, it offers exciting opportunities for your experiments. Let me explain very briefly what it does and what you can use it for by using an analogy. When you play a game, your computer needs to render elaborate graphic scenes at a very fast pace, and the computations involved in doing that are very intensive. So your computer uses a specialized piece of hardware, the graphics processing unit, or GPU, in order to carry out these computations quickly and efficiently. So likewise, you can create programs that perform inference tasks, such as image classification or object recognition. And again, those computations are quite intensive, so they require a lot of time and computational power. What the Coral does is it contains a specialized piece of hardware called a tensor processing unit, or TPU, that carries out these computations quickly and efficiently. So strictly speaking, neither the GPU nor the TPU are necessary, but they are essential in easing the load on the main processor and performing specific tasks more efficiently. We encourage you to check out the documentation, which is constantly being updated, but you should definitely also read our new project. Okay, thanks. which is about image classification using the Coral dongle. You will learn about the process and the programs you can use in order to train and use a machine learning model. In this case, the model will eventually be able to recognize whether an image captured with the AstroPi was taken during the day, night, or twilight hours. This is a simple example, but it will help you grasp the essentials. Now, we've already received quite a few insightful questions about the Coral, and I'd like to address a great question which was posed from Team Atlantis. I have broken it up in two and rephrased it, but essentially the team is wondering about the different ways that the Coral can be used within an experiment. So let me answer that. First of all, you can use it before you actually submit your program. You can retrain an existing model quickly in order to include it in your program. While your experiment is running, you can use the Coral to receive input such as images and quickly make inferences about the input. But also you can use it for post-processing. You can use it to process the data generated by your experiment and make inferences or retrain a model again. Interestingly, we've had a question from Pi heads. Let me just find that. There you go. That they ask whether or not they can use Google Colab during post-processing for making those inferences rather than the Coral dongle. And the answer is yes, they can. And it would be great if they could also share a link to their post-processing code for us to see. There's another practical question about how a model can be included in a team submission. And the answer is a model is just another file, and you are supposed to be able to include any files that are required for your submission within like a zip file. So you can just include it along with all the rest of the files. Richard, I'm going to hand over to you now for the photography aspect.
Thanks, George. Before I talk about that, I'm just going to answer one of the questions that came up after I was talking about hardware that I didn't see in time, which was, no, it wasn't that one. It was, it's all got this one here. Does the kit contain a heatsink for the Pi? And the answer to that is no, it doesn't, and you shouldn't really need one unless you're going to put it into some kind of enclosure. The Raspberry Pi 4s have had lots of firmware improvements since they've been released, so they're able to keep themselves nice and cool as long as you just leave them, with some airflow around them. I thought I'd answer that now. Back to photography questions. So so I think when we sometimes think about people taking photos from the International Space Station, we think about this: astronauts using their regular cameras and pointing them out of the windows of the cupola module here. That's not how the flight units are deployed when your experiments run in order for them to take their photographs. They're in a situation like this. There's a hatch, typically what's called a node window here, and the AstroPis are connected on an arm in front of that hatch and left resting there. So it's not a single big pane of glass like a normal window. That's all actually more like a porthole. And the space station at that point is a bit thick. It has a depth to it and some coverings on the outside that actually mean you're almost looking like down a tunnel when you're taking those photographs. And that has implications for what you'll see in your images. So for example, here is an example image from a previous experiment, from one of last year's experiments. A quick quiz for anyone in the chat, if they can identify where in the world that picture is. And while you're having a think and look at that, I'll answer some of the questions that we've been asked, particularly around getting hold of sample images. And listening to what George was saying earlier about machine learning models, you might well want to train a machine learning model with some sample images. And so we have actually made a set of images available. There's two places you can get them. One is wait for your kit to arrive, and on the SD card, there's a collection of the images there. But if you do want to get started, which we strongly advise you do, you can see the link here in front of you, rpf.io/ap-sample-data. And from there, you can download a zip file with a selection of images from a previous experiment in there. I'm just going to have a look if anyone's had a guess.
There was also a question about whether people can get images from the new Astro Pi, and I'm going to remind everyone of the date later, but they haven't actually launched yet. They're still on Earth at the moment. They're going up to the ISS later in December and will only be commissioned in January and February. And that's commissioning process is when we start to get the first photographs back. We may well be able to send some of them out as we get them to help. But at the moment, if you can just use the data that Richard's already mentioned.
Right, good point, Ollie. And I'm just going to talk a little bit about some of the differences between the images that you need to think about when you're working with some of those old images earlier. Now we've got a few suggestions in here about where this picture is, and some of Mr. Japalau has got it completely right. It's Lake Balkhash in Kazakhstan. Good work there, working out that. That's very impressive. Yeah, so if you look at a map, look at where Kazakhstan is, you can see it. This lake is actually the 15th largest in the world. It's a really big lake. And as you can see, it comes across really beautifully in those pictures from space. There's a normal satellite image. And you can see there the area surrounding it in Kazakhstan is pretty barren in terms of plant life and greenery, which is why it looks very similar in the pictures that were taken by the Astro Pi last year. But remember, the Astro Pis last year, all of the experiments were NDVI experiments. So they were all using the near-infrared sensitive camera with a blue filter over it, which means they don't actually look like the pictures you would normally see from satellite imagery. And again, I'm going to talk about that again in a second. The other thing to remember is that the orientation of the view you get from the window of the space station may not match up with what you normally see on a map. So you can see I've overlaid the picture from the space station with the map, and you can see that that's tilted quite a bit to one side there. And again, we'll show you a few more examples of that later on. Another thing to think about is what you're going to see in your 3-hour window. So I'm just going to play a movie to show you. Oh, Mark's done that for me. Amazing, Mr. C. So this is a time-lapse movie, and in here we've got a whole 3-hour window just in 1 minute. And so you can see it's quite jerky because the frames are taken quite far apart. And so we pass from the ISS being in daylight into it being essentially dark, what you might talk about as being nighttime. And you can see you can't see much there, right? There's some sort of faint green glowing, but generally you're not seeing anything of the Earth. Again, I'm going to talk about that in a minute. Now we're into our second daylight portion of the 3-hour window, passing over a lot of ocean there. You can see all the different clouds. Lots of teams this year doing experiments around clouds, which I think I'm super excited to see the results of. And then we can see we pass into dark again. So this is you won't obviously have them in exactly the same part of your 3-hour window, but that's the cycle you'll expect to get in your 3-hour experimental window. So just in terms of visualizing that's what your orbit might look like. And there's actually some software included in your SD card images you'll receive called Digicam, which will enable you to display those sample images that we've supplied so that you can get an idea of how it changes, how they change as you pass around the Earth in your orbital path. Here we go. Let's move it on. So I talked a bit about what you can see in the nighttime. One of the amazing things we saw last year for the first time was this picture, where you can see the International Space Station has passed over a storm. This was actually in South America, and the experiment, which was actually looking at clouds, managed to capture a lightning strike within the clouds. Now, that was great news to us because up until now, we've not really seen any evidence of being able to see things at night because the blue filter over the infrared sensitive camera obscures a lot of the light. We thought that it just wasn't sensitive enough to pick up light, but we've seen that for the first time. So if you did have an idea that involved nighttime photography, it does look like it's possible. The thing to bear in mind is over the years, we've had thousands of pictures taken at night, and this is pretty much the first one where we've seen anything like this. So the chances of being able to capture something maybe aren't that good. However, we've got new hardware going up this year. We've got a new camera sensor, we've got new lenses, and we've got much higher grade optical filters to enable the NDVI experiments to be performed. So it may well be that we do get to see much better pictures of cities at night illuminated from the International Space Station. As Ollie mentioned, when the new flight units arrive on the ISS, they'll initially be conditioned, and we'll be taking some sample pictures as part of that commissioning process. And in order to do that, we'll have to capture some nighttime images as well as daytime images. And if we can, we'll make some of those available to you as soon as we get them in the new year. Just another reminder about the orientation you can expect. Here's a wonderful picture of some of the Maldive Islands, and you can see they're scattered left to right across the image. If you actually look at the Maldives on the map, normally when you think about it, they're positioned north to south. So here again, the orientation of the picture needs to be swapped over. So if you're thinking about doing some kind of recognition program, remember that things may not be the way up that you're conventionally used to seeing them on a map. Another question we've been asked around is around the field of view for the new hardware. So this is the calculation that you may have seen if you've attended our webinars before for the version 1 camera. And this basically enables you to work out two things. First of all, what's the smallest size that can be detected by a single pixel? So how much does a single pixel in your image represent on the Earth? And you can see that value here. And also what the dimensions of a square picture will be. And so these are the values for the Mark I hardware. In terms of thinking about how much you can see from a pixel, obviously there it's a few hundred meters. So each pixel represents a few hundred meters. But if you zoom in at an image so you can see the individual pixels, you can see that you can't see those with great clarity. So like 120 meters is about the length of a football pitch. You can't see a football pitch within there. There are all sorts of things that will distort your image. Clouds, atmospheric distortion, the glass between you and the outside world. So although that is in theory the resolution of the camera in terms of what it can resolve, don't expect to see things that size in your images. In terms of the area that's covered, another quick quiz for anyone who wants to guess the location of this particular thing. Chuck it in the chat really quick, and we'll see if any of you guys can work that one out. But if I just move on to the next slide. I've given it away now, haven't I? It's in Egypt. So that's the Nile River. Anyone can jump in and give the answer now. Yeah, the Nile. Well done. Yeah, you got that straight away. You can see here that, again, you've got the orientation shift in there. And also, if we then look at that distance, you can see that the distance there roughly corresponds to what the calculation showed. Now, this is all to do with the old hardware. For the new hardware, there's a brand new calculation. And that actually depends on which of the lenses we'll be using. So the flight unit I showed you earlier has this 5mm lens on it, which we think is going to be the lens that we'll use for the experiments this year. And that gives the values that you can see here. So actually, we will be covering a larger area of the Earth with a single frame, and the size of each pixel will give you a smaller resolution on that side. We do have another lens that we're sending to the International Space Station, and that's a 12mm lens, which looks a bit different. You can think of that as a zoom lens. So here again, you'll be covering, if we use this lens, you'll have a smaller area that's covered, but the ground sampling distance will actually be higher. And just to visualize that, this is Malta, and I've drawn 3 boxes around it here. So the orange box will be the new hardware with the 5mm lens on it, which is what we expect to deploy your experiments with. You can see how that compares to the red box, which is the Mark I hardware. So you can see that it's covering a slightly larger area. And if we were to use the 12mm lens, you can see we get a much smaller box. But remember, you still got the same resolution in your sensor. So each pixel will be covering a smaller distance on the ground.
Richard, just to clarify, it looks like that picture is of Malta, but the island that's in the boxes is Sicily. We've just had that pointed out to us. The Malta is over. Malta's at the bottom. That's... Yes. It's very confusing.
I just read what it said in front of me. We got a couple of questions around this. So particularly, do we switch lenses in space? So no, you won't be able to request that your lens is switched as part of your experiment. When we deploy the AstroPis, they will have a particular lens on it. And the only switch that will happen will be changing between the flight unit that has the near infrared sensitive camera to the one that enables you to take photos in visible light. But we'll run those with the same lens on this year. At least that's the expectation anyway.
And we're going to be deciding which lens we're going to be using as part of this commissioning process. And we will be emailing out to teams once we're going to be learning so much during this commissioning process, as I hope you've got the impression. And so we're going to be in much more active communication with you, giving you updates about what we're learning about how the devices work. And so do keep an eye on your emails, because we will be emailing out essential information that will help you.
Yeah, and all that question I was just going to answer that. If you want to pop that one back up, please. So the camera has interchangeable lens, that's right. What aperture and focus is the lens set to? So for the 5mm lens, the focus will be set to infinity, because we want to focus on something that's obviously a long way away. And the aperture will probably be kept quite closed, because we don't want too much light to oversaturate the images. But part of the commissioning process will be to check whether those settings that we think are going to give the best images actually do. So if when we run our commissioning process, we find out that there's better settings, then we will let you know those. Also worth remembering, though, that the lens you get in your kits is a 6mm lens, of which there are also some being sent to the International Space Station, but it's not the lens that is going to be used for the life on Earth experiments. Great. Moving on. Oh, so finally there, you can see the extra length, if you like, that the new lens and new sensor gives us would make that old picture from previous experiments that much longer on the map of the Earth. Now, in terms of, we had a few questions about visible light and NDVI experiments. Just to give you some examples of the differences. So I've built a simulation of the ISS window in my house and tried to take some pictures using the different flight units. This is a picture taken using the Mark I hardware, using the near infrared sensitive camera with the blue filter over it. And the first thing you know is it looks like it's upside down. And so all these pictures are taken at the same orientation, which is with the flight unit basically this way up. So there's a bracket at the bottom of it, and it's that way up in my window, which is why this one's upside down. We've also had quite a few questions about file sizes. So I can find some of those questions. Some questions around file sizes. What is average size of a photo? So the typical file size is 2.5 megabytes for the old flight units, for the Mark I hardware. For the new hardware, it's slightly different. So here's another picture taken with one of the new AstroPi hardwares. You can see, first of all, it's the right way up. The file size is much bigger, 6 megabytes. And this is using the visible light camera. And then there was also some questions around the different types of camera and their sensitivity. And all of this information is available online. If you go to the Raspberry Pi documentation, and there's a link at the bottom of this slide, you can see all the different resolutions and the different sensitivity of the cameras laid out there. Don't forget, the Mark I hardware uses the version 1 camera. So it's this one on the left, and the high quality camera, which is what's in the new hardware, is on the right. So you can kind of ignore the version 2 camera, unless you're a recipient of an AstroPi kit from previous years, in which case you will have a version 2 camera with that kit. So now let's talk about NDVI finally. So this is the new hardware with the 5mm lens on and the IR sensitive camera with a red filter. So that's a big difference. The new hardware uses a red filter instead of a blue filter. We did a lot of tests to work out the best way of getting really accurate NDVI calculations. And everything that we tested showed us that using a red filter rather than a blue filter which does alter the NDVI calculation slightly, gives you the best results in terms of evaluating plant health. So you can see, if you compare that to the old filter there, the colours are very different. These are the same trees in my back garden. You can see with the old blue filter on, they've taken on this kind of yellowy colour. But with the new red filter, they're almost a turquoise blue in there. And just by comparison, that's with the 5mm lens, and then this slide here is using the 8mm lens. So you can see, particularly, you lose this porthole effect because it's a zoom lens. It zooms down the center of that tunnel, if you like, and gives you a much less obscured view. But obviously, there's far less in the frame, so you're seeing less of what's outside using that view. And then finally, just to give you an idea of the colors you might expect to see, sky's blue normally, but with the red filter on, it takes on this lovely sort of orangey color. So I think some of the photos taken with a near-infrared sensitive camera from the ISS are going to be pretty spectacular and different. But if you are looking at photos taken from the sample images, remember they will be different in terms of the color channels that you might use for NDVI. If you want to learn more about NDVI, we have a great new resource, which is this project on our website at the link here, rpf.io/NDVI, which takes you through the process of understanding about NDVI and how to take really good NDVI readings using the Python Pi camera library. So if you're doing an NDVI experiment, I strongly recommend taking a look at that. And now I'm going to hand back over to George, who's going to talk more about the process of creating your code.
Great. So in the kits you will be receiving, you will find an SD card that contains the desktop flight operating system. This is the environment you will be working in while developing and testing your program. All the system packages and Python libraries that are installed on the actual Astro Pis are also installed in this environment down to the same version. So if your program works in the desktop flight OS, it will also very likely work when it is executed on the actual Astro Pis. And if your program raises errors when you test it in the desktop flight OS, it will most likely fail our testing process and will not achieve flight status. I will briefly walk you through some of the main features of the desktop flight OS to give you an idea of how you can use it. First of all, under the programming menu, you will find several different IDEs or development environments. This is software that you can use to write, edit, and run your code. And in this particular screenshot, I'm running Thonny, but there are also a few other options available. Also in the programming menu, you will find the SenseHat emulator, and you can use that to feed arbitrary sensor values to your program so that you are able to test it under any conditions you like. In fact, this is a special custom-built version of the emulator that also allows you to control the values for the new light and color sensor. The desktop flight OS also contains sample data from a previous mission that you can find in the data folder. Like Aldi and Richard mentioned before, you can also download that data from that link on the slide. So you can start working on that before you actually receive your kit. So the data includes sensor readings in a CSV file, as well as images captured with a near-infrared camera. You can explore this data to understand what sort of readings to expect when your experiment is running. And you can also use it to test your program or even train a machine learning model. And this is something some of the teams have already asked about. However, you need to remember that this data was obtained using the previous version of the Astro Pi hardware. There's no motion, light, or color sensor data. And the images were captured with the first version of the Raspberry camera, like Richard said, with different capabilities. So when the new Astro Pi flight units are deployed on the ISS in January, we plan to run a data collection program and share the results with the teams. And that way you can have more up-to-date samples to work on. Another relevant thing you can find in the desktop flight OS is an image processing program called Digicam. And one of the features it offers is the ability to place images on a globe, provided these images contain geolocation data. So you can try out this feature with the sample data, but you can also use it to test that your program includes geolocation data with the images it captures. You can also, when you receive your own images from the ISS, you can again use this feature to quickly locate images that might have been captured above specific areas of particular interest to your experiment. So before submitting your finalized program, make sure you have tried running it directly from the terminal using the command that you can see on the slide. This is more or less the way your program will be executed when running on the ISS. You need to make sure your program runs without errors in the desktop flight OS. If it fails to run in the desktop flight OS, it will also fail during our test and it will not achieve flight status. Also, make sure you allow your finalized program to run for the full 3 hours. It's not uncommon for programs to fail well into their allocated execution time. Now, very often teams will ask us if a specific Python library or a specific version of a library will be available when their program is executed. Now, you need to remember that the Python environment in the desktop flight OS mirrors the one on the ISS. So the best way to answer this question yourself is to just fire up Python and try to import the library. If you're able to do that, the library will also be installed on the Astro Pis as well. If not, contact us so that we can discuss possible alternatives to the library you need. If you install software updates or additional system packages and Python modules, your development environment will no longer mirror the one on the ISS. So if you choose to do so, your program may run successfully in your modified environment, but it may raise errors when we try to test it. So always test your finalized program on the original version of the desktop flight OS. In the phase 2 guide, you will find a link that you can use to download a fresh image and burn it on your SD cards. One resource I have found extremely useful is NASA's live video stream from the ISS. It incorporates ESA's ISS tracker, so you can check if the coordinates your program calculates for the ISS agree with the ones provided by the tracker. But the live stream can also confirm your program's calculations about whether it's flying over locations where it's day or night. And since the view offered by the live stream resembles what the Astro Pis will be seeing, you could even point your kid's camera towards it while you're testing. Richard did something similar. He's good with simulations, as you've seen. He did something similar last year when testing Life on Earth submissions. He pointed the cameras of his Astro Pi replicas towards a stop-motion animation created by older Astro Pi images. Speaking of testing, we thought it would be interesting and useful for you to get an idea of what happens to your programs once they are submitted, what sort of process we go through in order to test your programs and decide which ones will achieve flight status and run on the ISS. Now, as you can see, it can be summarized in 3 steps, and I will go over them in a little more detail. First of all, before running your code, we inspect it. Generally, we scan for specific patterns or imports that might indicate that one of our requirements is not met. If there's a match, we manually inspect the code more closely to confirm whether or not there's an issue there. We are especially mindful of security, so we also employ special purpose software to analyze the code and augment our security tests. I don't think we have time today to go into the details about how we check for specific requirements, but please make sure you carefully read and understand all the requirements that are listed in the Phase 2 guide. Also, it's a very good idea to use comments in your code to explain how it works. Helping us understand your code when we inspect it goes a long way. Now, if your program passes the first set of static checks, we try to run it. And initially, we schedule it only for a few minutes just to see if it raises any errors or exhibits any unexpected behavior. It's only the 3rd time around that we actually schedule the program for the full 3 hours. And if it completes the run successfully, we inspect the kind of data it generates. And again, we search for specific signs or unexpected or unwanted behavior and check that all the requirements are met. We even try to transfer the data that your program generates through a specialized system that simulates the link between the ISS and the ground stations. Unfortunately, the Astro Pis get allocated a specific amount of time on the ISS to run Mission Space Lab experiments, and this poses a hard limit to the number of experiments that we can run, which means that some of your submissions might not achieve flight status even if they pass our checks. So in the 3rd step, we use a set of judging criteria to award flight status. We favor experiment feasibility, the extent of documentation, code quality, etc., etc. I think, oh, sorry, I missed a slide. If your experiment achieves flight status, it will be scheduled and run on the ISS for 3 hours. Remember that the ISS orbits the Earth every 90 minutes approximately. So in the time your experiment is executed, there will be 2 day passes and 2 night passes, much like you see in the picture from the ISS tracker and Richard's shown before. There's no way to know in advance the exact time your experiment will run, and there's no way to arrange for your experiment to take place at a specific time over a specific location. I think it's time up to move to some of the questions that have been asked.
George, some questions just come up about when you were talking. How often does the ISS go into night? There's one question that's come up.
So there's a 90-minute orbit, which means that within those 90 minutes, approximately half of that will be a night pass. Sometimes it's a little longer, sometimes it's a little shorter, but it's usually around 45 minutes.
And as we saw on that time lapse I showed earlier, they're spread out at even intervals throughout your 3-hour window, right? Here's another one for what you were talking about geolocation and how can we include geolocation data in the images?
So it's not included by default, but there's a very detailed section in the phase 2 guide with a code you can use to do that. But it's good that you actually test that the code works. So it's a good idea to test that data is included in your generated images.
Great. And where can we download the Flight OS from? There's a link in the phase 2 guide, right?
Yes, exactly.
So everything you need to know is normally in the phase 2 guide. That's definitely the first place you should look. And there is a link in there so you can download the Flight OS now. If you've already got a Raspberry Pi, you can install that and start work as well. Here's another question here about TensorFlow, going back to the AI stuff.
So let me just read that. I was wondering. The TensorFlow is already pre-installed, but you only really need it if you want to develop and train models. So what I would suggest is if you want to build a new model and train it yourself, you can do that on a different machine or on a Colab and just download the model that you can use on the Coral. You don't really need TensorFlow on the Raspberry Pi to train and develop your model.
Here's a good question about testing. Will my program be disqualified if you put in a little Easter egg?
I would say it depends on the Easter egg, but let me give you an example. If your program is a life on Earth experiment, you're not allowed to use the LED matrix. So if that Easter egg results in using the LED matrix, then yes, it will be disqualified.
And here's an interesting question. Will a program that intentionally uses all of the device's memory be accepted?
Of course not.
Yeah. Here's one here. And machine learning is possible. I think what they're asking is, can you do real-time stuff with the Coral dongle on the ISS?
So the best way to approach that would be to have a pre-trained model included with your submission and use that model to classify images or do any inference tasks that are possible live using the Coral dongle. So yes, you can use the Coral dongle to draw inferences and perform machine learning tasks, but that would probably use a pre-trained model.
Cool. Here's another good one here. Oh, there's too many questions coming in. Is the Raspberry Pi fixed to something, an inner wall, etc., or just left afloat? So for life on Earth, for those experiments, as you saw back in the slides I showed, it sits on a thing called a bogan arm, which fixes it into position so it can't float around. Inside the Columbus module for life in space experiment, the same thing is true. They're fixed to something that holds them steady. We have had incidents in the past of astronauts bumping into them, so it may be that it will move during your 3-hour window if someone touches it, but they're not just floating around. No, for sure not. We are going to create a 3D model using data from the accelerometer and data and altitude that we record. We make this model in phase 4, does it in phase 3 in real time? I'd say that's kind of up to you. It sounds like a thing to do post-processing to me. So to collect all your data and then build it. When you get the data back, you can then write up and report in your phase 4 report. This question here, if you only take pictures while it's daytime, you can max out the memory if you take pictures every 3 minutes. I think you mean, by memory, you mean storage, so how much space you use up on the disk. So that's right. So if you've got a 6 megabyte image, you need to calculate how many of those you can record before you exceed the 3 gigabyte limit on the Raspberry Pi. Also worth remembering, though, that the file size of an image does depend on how much detail there is in the image. So if you take a picture of a blank white wall or black of night, that image file size will probably be smaller than a really detailed picture with lots of information on it. But do test your code, make sure you're not doing things that will exhaust your 3 gigabytes. And will NDVI images work through clouds? You'll still be able to collect the same data. You'll still be able to get the near infrared light and the other visible light that the filter passes. But obviously NDVI is really about plants. So you need to be able to see something green, essentially, in order for you to do an NDVI calculation. If you can't see anything green through the clouds, then you won't really be able to make an NDVI calculation. Do electronic devices on board the ISS interfere with the Pi magnetometer? That is a great question, and that sounds like a really good experiment that you could run as part of Mission Space Lab. As part of getting the hardware qualified, we have to do a lot of tests to make sure the Raspberry Pi itself isn't affected by other electromagnetic radiation that there may be on board the ISS. But the magnetometer itself is obviously a sensitive device, so if an astronaut walked past with something that was big and magnetic, or even a large metallic thing, it may well affect the results you get from your magnetometer. Yeah.
We had a question that was sent in beforehand from Camper's team. They have 2 teams from the same school. Congratulations. And we're only sending out 1 kit per mentor. That's true for everyone. You still submit 2 separate projects. You don't have to amalgamate them, and you'll just need to share access and work out access to using the Raspberry Pi. Remember, you've got the emulator, so that perhaps while one team is working on the Raspberry Pi itself, the other team can be developing their code on the emulator, and then you can swap for testing purposes. There was also a question about whether the glass of the window in front of the Astro Pi filters the light and affects the amount of IR radiation. Richard, do you know whether we have been able to test that?
We haven't. So there's quite a lot of material between the sensor and the light that's coming from Earth. So there will be some attenuation of that light. The glass on the ISS windows doesn't by default do any additional filtering, but if you look at any pane of glass, it will have some IR absorbency. But I wouldn't worry about it for the purposes of your experiment. There's some questions about Skyfield here, which sound like they're made for you, George.
I have recorded some other questions as well, so maybe towards the end when we cover them, I will have like 3 or 4 minutes to address Skyfield specifically.
Okay.
This is something we've mentioned before, I think. You can definitely choose to just collect data and process it later on. If you want to run it through a machine learning model, it's just fine. You can do that during post-processing. Do you think perhaps we could move on to Skyfield, or do we have any
Yeah,
other?
let's do that. Let's do that. Some more questions
cool.
coming in.
So this is probably, I'm going to just give a slight introduction for the teams that have participated also in the past, and they were used to using a specific library called FM. This has now been replaced by another library called Skyfield. So we received a few questions about that, and I'd like to answer them now. So both the older library FM and the new library Skyfield are used for performing astronomical calculations. One of their main uses in AstroPi is for computing the location of the ISS given the current time and up-to-date telemetry data. So you can see why it's so important to use them, why their use is very central to AstroPi. So in the past, teams had to retrieve the telemetry data themselves and include them in their code, like you see on the slide. So they had to start their program using those 4 or 5 lines to eventually create an object called ISS and use that to calculate the ISS's location. This is no longer how things work. We offer a simple Python module called Orbit. This uses the Skyfield library to greatly simplify how the ISS object is created and how telemetry data is used. So from now on, the FM library will no longer be available. Any code that uses the FM library will have to be replaced by new code that uses Orbit or the Skyfield library directly. Let me just move on. So a couple of teams are asking about how it's possible to know whether or not their experiment is currently running over a region where there's day or night. And I included this question here because it does have to do with computing the ISS's location. There are many solutions to this, and we suggest a very simple one in the phase 2 guide that involves using the isSunlit method from Skyfield. This will return whether or not the ISS is in sunlight. But the sun rises a little earlier on the ISS than it does on Earth, and it also sets a little later. So this method is not completely accurate. It's accurate enough in the sense that it will never reject daytime pictures. It will never tell you it's night when it's day. If you want a more accurate solution, check Skyfield examples and documentation to see how you can piece together a piece of code that computes the sun's elevation at a given point on Earth. I'm not going to go deeper into this. This is something you need to research as part of your project. I have another question from Team Astro. Essentially, I've run across this problem myself, and it's kind of an interesting way to solve it. So suppose you have a program that behaves differently depending on whether or not it's day or night. The question is, how can you test that program efficiently when the ISS crosses the day-night boundary every 45 minutes? Are you supposed to wait? The answer is no, you don't have to wait for the ISS to reach that boundary. Essentially, your program computes the current position of the ISS based on the current time. So if you change the system time, you can trick your program into thinking it's at a different position. So by changing the time, you can check whether it's flying over day or night. A couple of teams have actually tried the Skyfield library already, and they have noticed that at some point it might need to download something from the internet. So you obviously can't use the internet or any networking while your experiment is running on the ISS. But if your program requires what is called an ephemeris, which is a data file, it will download it from the internet. You can do that while you're developing your program, and you can actually include that file since it's necessary for running your program. You can just include it in your submission. That will be fine. We will take care of the rest after that.
Some more questions on sort of Python-y stuff, George. Is this one, what exact version of Python will the Raspberry Pi be running?
So it's 3.7.3. And if you want to find that out, just look at the version of Python installed in the desktop Flight OS. All the versions of the Python modules and Python itself are the same on the desktop Flight OS and on the actual ISS modules.
Right, and it's probably worth mentioning, if you're already familiar with Raspberry Pi and you use them a lot, one of the standard things you would normally do is to update and upgrade your software. When you get the Flight OS, please don't do that, because you may find that you bring down later versions of applications or libraries that are going to be available on the ISS. So to make sure you stick with exactly the same versions that will be on the ISS, that will be there for when your code runs, don't upgrade or update that Flight OS. Here's another question about code compatibility. So is all the code they wrote last year compatible with the new hardware?
One thing that will definitely not be compatible, and it's not the hardware, it's the new software, is whenever you use FM, you need to replace that by like use of Skyfield and Orbit. In general, though, I would expect that most of the things, unless they're really elaborate or depend on a specific Python version, should be compatible. Right. I know things have changed. For example, in OpenCV, there are some things that might not work anymore, but it's like more specific details. So in general, the answer is they would mostly work, but anything using FM will definitely not.
We've had a few questions about where someone has entered multiple teams and they only will be getting sent one kit, about how they should work. Do you want to cover that, Ollie?
I can repeat what I already said, which is that they need to share access to the device. They still need to submit 2 different programs for each team that got through, and while they're working out access, they can use the Trinket emulator to run their program.
And so, how many teams will be able to participate in the 3rd phase?
Yeah, I was just about to get onto that. We can't yet say how many teams. We can't give a definitive number. It depends on the number of Life in Space programs that we have versus the number of Life on Earth programs. It depends also how much time we can negotiate at the window, and the balance between visible light and IR light projects. So it will, unfortunately, that's one of the sort of calibration things that we need to do in that testing process that George was talking about between phase 2 and phase 3.
Okay. There's a question here. We may not use the visible light camera or the LED matrix during the experiment at all. We will be rejected from getting into phase 3 if we choose to do this.
It depends if that's Life in Space on Life on Earth, doesn't it?
Right, exactly.
If you're, that's fine.
Yeah, if you're Life on Earth, then part of those experiments has to be taking pictures of the Earth using the camera. And that was definitely the most popular theme this year. So we wouldn't want to put any experiments through that weren't actually making use of the camera.
Before we go, I just want to remind everyone of the dates. So you need to submit your code by the 24th of February next year. Before that, though, we've mentioned that the flight units are still on Earth. They launch on a SpaceX rocket on Tuesday, the 21st of December from Kennedy Flight Center. We will be emailing you all to remind you of the rocket launch, so you can watch along. But yeah, do submit your code by the 24th of February, sorry. Your code then runs on the ISS. Phase 3 happens in April and May, and you will have your results returned for you for analysis in June and July. I just want to give a shout out because we've had so many people saying hello. We've had people from Germany, Sweden, UK, Greece, Italy, Romania, Poland, Spain, France, Switzerland, Netherlands, and Denmark. Hello to you all. It's very nice to have you here.
Yeah, it's been really great to see all the lively comments in the chat and to have so many questions. If we haven't been able to answer your question because there were huge numbers in the chat, please do use that email address to send us the question in, and we'll do our best to get back to you as soon as we can.
Thank you so much, everyone.
Thank you all. Bye-bye.
Yeah, thanks a lot. Bye-bye, everyone.